Hello, this is Research Team 9, and we'll be presenting our project on computational cardiovascular fluid dynamics. One difficult decision that neurosurgeons must make today is determining the best treatment for brain aneurysm patients. The limitations of medical imaging results in a lack of quick and accurate data that can be gathered from the patient. Our goal with this project is to be able to run patient-specific simulations on the blood flow in and around aneurysms to collect critical information that can be used by medical professionals to make better evaluations.
Through the use of 4D flow MRI scans, which visualize the vessels and blood flow in the body, patient-specific models and digital meshes were generated to predict the blood flow within the brain. To make the predictions, assumptions based on fluid dynamic principles, such as how fluids react in pulsating flows through pipes, in the one-mersive profile shown here, were applied to the simulations while bulk flow measurements were obtained from the 4D flow MRI data. Through this incorporation, realistic patient-specific data can be generated for clinical applications.
Throughout this summer, we performed many different simulations to understand the blood flow in cerebral arteries. These simulations gave each of us a solid understanding for when we moved on to the more complex simulations of large networks of vessels. The vessels we are analyzing are understood through a comparison to an electric circuit. Through this analogy and understanding of pipe flows, we are able to model vessels and collect accurate resistances for these simulations. We ran the simulations using a program called Computational, in which we created 3D models of the vessels, generated computational meshes in which the simulations would run, and finally adjusted the simulation parameters to ensure that the calculations are comparable to a vessel in real life.
Once the data files from the simulations have been obtained, we perform a verification process to ensure the consistency of our results. Two tools that we use to do this are ParaView and MATLAB. ParaView provides a visualization of the various flows we are investigating, which acts as a qualitative check in our process. We then expand this through a series of quantitative checks using MATLAB scripts. Using these programs, we determine the CFL number, the periodicity, and residuals of the simulation, which we compare with a given acceptable data range to prove that our data is accurate. We also perform a grid independent study to determine whether the mesh sizes used in the simulation are suitable. Once all the checks have been passed, we then know that our data is accurate.
The above images presented are a visualization of streamlines in two different simulations, one through the left internal carotid artery and one through the anterior half of the circular villus. These results depict vortices formed in the aneurysm, which lead to a higher shear stress and lower pressure in the aneurysm. Similar to this, the simulation results provide us with detailed information on the particular vasculature in interest. The simulations were also verified using advanced post-processing, mainly focused on grid convergence for pressure drop across the inlet and the outlet.
These results can be used to provide a more accurate clinical predictions, as the physician does not have to rely on personal experience alone. They can use the patient-specific model, which takes an algorithmic approach to indicate if the patient has any troubling signs, allowing for an earlier medical intervention. The end goal of the patient-specific model is to use data to diagnose patients earlier and more accurately instead of having to only rely on physician intuition. Thank you to the Mechanical Engineering Department for setting this up and to all the sponsors.